Welcome back. This is example one from one a day 3. As you can see here, section 1.3, continuous data types. And then so in this example, we're going to look at a set of baby Ruth's candy bars. There are 40 measurements of their weight in grams. And we're going to try to calculate the sample mean and the sample variance for this group data. To do that, we're going to input each of these data points into GeoGebra, and then we're going to use those tools in GeoGebra to compute all of the required goodies for this particular problem. All right, so let's jump over to GeoGebra and start with that process. All right. All right, now that I have all the data inputted in, I want to calculate the sample mean and the sample variance. So the first thing I'm going to do is I'm going to create a list with this data. I'm going to highlight all of this and go down here and create a list. Okay, and that I'm leaving off the label there. Okay, and now I want to sort the data. So GeoGebra works best with sorting lists. And so if I sort the list, then you can see here, this will sort them. Default is from least to greatest. So that's very helpful. Now I want to calculate the range. So I'm going to take the max of L2, and I'm subtracting the min of L2. And so that difference is 6.2. Okay. So now to compute or to create the bins that we need to have equally spaced bins. So how can we divide up a difference of 6.2? Sorry, create a sequence of bins that would cover that distance of 6.2. So you can divide it by any number. If you think about multiplication, 9 times 7 is 63. Or so 9, if we make that 0.9 times 7, so 0.9 times 7 is 0.63, which would be really nice because with that, then we can deliver, or we can divide that extra tenth uh, in half and go a little bit above and a little bit below the starting bins for this data range. And so let's do that. So we're going to take this value and we're going to take 0.9 times 7. So we're going to have 7 bins. Each length will be 0.9. And we're going to divide that by minus A. And then we're going to divide that by 2. So that gives us a fifth or 5/100ths on each side for the bins. Okay. Notice that we could choose any value we want for the bins here. We could choose when I say bins, I also call them classes, right? They're also called classes. So we can call them, they have a different language, but those are the idea. We're trying to figure out how big are the gaps that we're going to try to put in for each of these. All right, now that we see that the little extra wiggle room we have with our 7 bins of length 0.9 gives us a little bit of wiggle room, if you will, on the class intervals. We have established our class limits with our sorting here. And so we can create the class limits more effectively by utilizing functions called classes from GeoGebra. And we're going to sort in here our L2. And we do want a total of 7 classes. And notice that we have 3 significant digits. So each one of these ranges becomes then we will make the approximation to 3 digits or 3 significant digits. Okay. We'll utilize and then NECA recognize also too at the class interval to give us that little bit of a tenth of we're going to subtract 0.05 from this limit for the lower range of the class interval, and we're going to add that same amount on this end. That way, each of the bins are given that equal length of 0.9. Okay, so let's jump over here. Okay, so after computing the classes here with our data, we're going to set these in, and that's going to be our class limits here. So this is going to be 20.5. These are the lowest and highest values of actual data in this range. So this is going to be 20.5 minus 20, not minus, that's going to treat as a 20.5 to 21.3. This is the range. Okay. And so we're just going to keep, it's going to be 21.4 to 22.2 equals to 22.2. We have 22.3 to 23.1. We have 23.2 to 20.2 to 24.0. Then we have 24.1 to 24.9. And then we have 25.0 to 25.8. And last but not least, we have 25.9 to 26.7. Okay. I think there was a that one was 24.1 to 24.9. Okay, there we go. So there's our class limits. Again, these are the lowest and highest values of actual data from our values in that range. Let's compute then our, well, like I wanted to make a computation out of it, 25.0 minus, not minus 2, 25.8. Okay. So seriously, wait. 25.9 to 26.7. Okay. All right. So this is going to equal our lowest value, which was 20.5. And we're going to minus it at 0.05, which that value was B. So we're going to minus B here. 20.5 minus B. There we go. And then here, this is going to be the same as that. So D is going to equal D, no, sorry, C2 plus 0.9. Okay. And that's exactly what we need. And then this is going to equal in 0.9, because again, that's our width or distance that we're looking to be. And if you're wondering where the B came from, that was the little extra that we had to add on, subtract on to make our 7 bins fit in our data. All right, so now we're going to have C2 plus 0.9. And this is going to be a D2 plus 0.9. Okay, so we can hold both of those down. And there's our classes. Okay, so now we can figure out our tabulation here, because this is going to equal the count. Just when we're going to count if, let's see, we want D2 is less than X is less than D2, and we want that from L2. It's going to give us 5. So this is the value of C here. I wonder if I can do it directly here. So let's go count if. Let's see, we have C3 is less than X is less than D3, and then L2 Okay, all right. So maybe if I just pull this down, that'll give us all the counts. And so this should equal the, let's try this out. This should sum, oh yeah. If you're really familiar with um, F2 to F, let's say 9. Oh, right. It's got to come over here and hit sum. So 40, and that is the number of elements. So this is the total. So that means that we do have them all accounted for. That's super exciting. And now that's helpful because now we can take uh, F2 and divide it by F9. I'm going to hit F4 here. I'm going to put that in the dollar signs here free that value. So that way I can drag this down and it should be the same for each of these. F4 divided by, yep. Okay, so that is perfect. Those are the exact values that we're looking for. And then class marks is the midpoint of D2 and D2. Let's see, let me do that midpoint. Dual, D2 to D2. D2, D2. All right, well then let's just do it the old-fashioned way. So this is going to be uh, um, hold on. All right, so this is just going to be C2 plus D2 divided by 2. And so this will be the class marks. This is the midpoint of each of the, okay, and so those are the class marks. All right. Now that we have all of this information, we can calculate the relative frequency histogram, should we choose. And then also we can compute the sum and the average of these. So, so let's go ahead and continue with that plight as we're here. All right. So maybe I'll continue these down here just so we can kind of get it all on one page. All right. So the class marks. I'm just going to continue that class marks, which is what we saw earlier. So this is going to equal what H2. Drag that down. Okay, perfect. And then over here, we're going to have the frequencies. And that's going to equal F2. All right, back on track for the frequencies. And so now this is F of Fi times U of I. So the process here is essentially the exact same as in the discrete case. So what we're going to do is we're going to take C14 and multiply it by D14. That gives us this value here. Okay. And then we're gonna add all of those up. And here, we're going to add all of these up. And this again should be 40, which okay. And now we're going to look at f of I times u of I squared. Okay, so this is equal to, let's see, equal C14 times D5 times D5. The calculation here is going to be C2 times C2 times C14 times C14 times D14. This is the UI squared, and that's the f of I. There we go. And so if we pull that down, okay, and then here, we're going to want to sum that. There it is. And then let's calculate the f of I times the u of I minus the average of u of I squared. Okay. To calculate this then, we needed the average, and so I just took this value and divided it by that. That would give me the average of 23.51. And so here, this is just going to be C14 times parentheses. What do we have here? We're going to have this term. Oops, I forget. Yeah, well, it will be this term minus this term, and that quantity squared. Okay, so let's go ahead and do that. We have C14 minus, and I want to freeze this in E23, and then I'm going to square that whole thing. Let's see. Let's try that one more time. This is going to be this cell, so it's going to be D14 times parentheses C14 minus E23. Let's see, and then square that. There you go. Don't know what I put in wrong last time, but it should have been like 30-ish something, and so there it is. And if I carry that down, okay, and so those are all of the values that we're looking for. And now finally, if we sum this, this gives us then that value, and so then the variance, of this thing, we'll call it f, is equal to, and so here we're going to take this value, which is G21, and we're going to divide it by parentheses D21 minus 1. For unbiased sampling, we need one less than the number of total values. And so if we do that, we get that the variance is 2.567, 2.5671. And then if we wanted to, we could also calculate the standard deviation of s is equal to, this would equal to the square root of E25, which is 1.062. 1.6022 grams. So that means that the average, we would expect that on average, these candy bars were 23.51 grams with a variance of 1.6, or sorry, with a standard deviation of 1.6 grams per. All right. All right, now that we have the average and the uh, variance, let's construct a histogram real quick. So we can just take the frequency total here, and we can make a list of those objects. And then we want a class, which we did earlier. So our list L3 here and our list L4, we can create a histogram by typing in the command histogram. And then if you click the right, you can see there's different options here. We want a list of categories and a list of heights. And so we're going to have L categories or the classes. So that's going to be L3, and then the heights will be L4. We hit enter then. You'll see the number that comes up here. And you can see the value there. That's the area of the histogram. So we'll hide that for a second. And so here's the image of the histogram corresponding to the heights here. And then if we do a relative frequency histogram, which will be helpful later on, you would do the exact same thing, but you would plot the heights of the relative frequencies, which are the h of x's here. One thing to note is that these numbers are not divided by n, the total number. These histogram values are related to, since it's a continuous case, h would be equal to the value of the frequency, we're calling it fi, divided by n. So in this case, that would be 40 times the difference in each of the values. So c I minus c to the I minus 1. In other words, what is the length of each of the bins? And so for our case, we have this 36 is the 40 times, right, the bottom part is 40 times the difference in each of the intervals. In other words, how long is the interval itself is 0.9. And so if you see 40 times 0.9 gives you the 36, which is the value that you would then use as the denominator for the frequency here. Okay. All right. You will notice that if you do plot them, they should also be the exact same shape. They will just be scaled proportionally due to the division. Okay. I think that covers all the major ideas in using both this technology tool and then also how to create a histogram, look at the computation of the sample mean, sample variance, and sample standard deviation. Okay, I hope that was helpful, and I'll see you in the next video.